what is the
Mm-hmm.
algorithmic thinking? How do you
Yeah.
frame the steps in a procedure, and which one is more efficient compared to others? And I think that's still relevant, because even
Mm-hmm.
though these language models are getting better at coding, they're still going to be guided by us, right? And so I think of this as
Yeah.
now a higher level abstraction. Just as now we are not coding in assembly
Mm-hmm.
anymore, right? We were in the very early days of computing.
Yeah.
We've been building higher level
Correct.
abstractions.
Hi, everyone, and I'm really excited to have a very special guest, Anima Anandkumar, with us today. So, Anima, welcome to the show. For those of you who don't know, Anima is a Bren Professor at Caltech and Senior Director at AI Research of AI Research at NVIDIA. So, really excited to have you, Anima. And I think there is so much to learn from you that I would just want to, spend most of time listening to you. So, welcome to the show.
Well, thank you for having me, and thank you for all the good work you do and making AI and other technical topics accessible to the wider community.
Great, thanks, Anima. So, Anima, I would just want to start with your, early days, and so you come from a family of, mathematicians and engineers. So can you tell us a bit more about, your childhood, and then when did you kind of develop the interest in the quantitative subjects, and then what was it in your kind of early days, and then leading all the way up to your research?
Yeah, I was very privileged to be in a family that encouraged learning and exploration and curiosity driven, just
Mm-hmm.
approach. And my mom is an engineer. In fact, she was one of the first engineers in the community, and went on a hunger
Oh,
strike for 3 days because,
wow.
she really wanted to do it. And my grandfather was a bit hesitant, although he's himself a math teacher. He was worried
Mhm.
about what, his relatives giving him advice that if my mom would be marryable or not. But then, he
Wow.
gave in, and the rest is history. And so my
Mhm.
mother always, inculcated that love for maths and sciences, and what there
Mhm.
wasn't that gender segregation or separation of the interests, right?
Wow.
And especially after my brother was born, we would just all work on like Lego and all kinds of building toys. And my parents
Mhm.
run a small scale factory manufacturing automotive parts. They brought some of the first computer numerically controlled machines to the
Oh, wow.
factory. And so I
Mhm.
looked at programming through that lens. Like, programming
Mhm.
isn't just something that happens on a computer in the virtual world, right? But you see,
Wow.
like, that physical impact, the big
Mhm. Mhm.
machine using these massive parts, and all of this process working in a seamless way.
Very
And that was that
interesting.
was just great. There was a lot of hands-on learning, seeing engineering, seeing electronics, but also
Mhm.
the mathematical concept. My grandfather, really like kind of would teach us math, and I would always tell him, "No, teach me more advanced ones. I want to be challenged
Oh,
further."
wow.
Uh,
Mhm.
and even my grandma loved puzzles, and so that was fun. But at the same time, it wasn't just like, oh, you only need to do technical things. I love dancing. I started dancing
Yeah.
when I was only 3 years old. I went to a Bharatanatyam class, and
Oh,
the
wow.
teacher was like, "No, you're," she's probably too young.
Mhm.
She cannot keep up. And but I
Mhm.
just apparently, went to the
Oh,
front of
wow.
the line, just started following all the instructions. And I love
Mhm.
dancing. And and they're not mutually exclusive, right? Dance is
Yeah,
mathematical in so many ways. So yeah,
it
I
is.
mean, I
It
had
is. Mhm.
great exposure to different things in my childhood, and I'm so thankful.
And when did you get exposed to computers and programming? And any specific instance or moment which you remember? about early days with computers.
Yeah, from even, right, growing up in the 80s, even from the earlier days, like of my childhood, I remember seeing computers. But then
Hmm.
towards the last part of the 80s is when they got the CNC machines. So at that
Right.
point, the computers wasn't just for playing some simple games,
Yeah.
right? It was bigger than that,
Hmm.
and it also made it. Less abstract in the sense, oh, these are not just like pieces of code you're forced to memorize. And if you recall the computers at that time, the
Yeah.
programming wasn't so easy, right? But within the machines it
Correct.
was much more limited set of instructions, and at the same time you needed to think about geometry. How would you make this
Yeah.
machine move, how to make sure the turret doesn't hit the component. So there
Right.
was a lot more of uh, aspects beyond just writing the program code,
Hmm.
and also all the electronics of it, and how these come together. So I think that really helped me with what I do now, to think things interdisciplinarily. So not just say,
Wow.
oh, I'm only going to worry about this part because
Hmm.
you know that
Yeah.
I'm not going to limit myself. And we didn't grow up that way, and that was just great.
Wow, great. And then you decided to go to IIT Madras at that time. So, I mean, was that the natural choice, or you considered any other options at that time? And then, what stream kind of did you pick on, and which areas did you kind of focus on?
Yeah, yeah. My dad is also an IIT alumnus, and yeah, he always said, "Look, there's so many amazing professors there, and
Hmm.
again, there is the emphasis on an interdisciplinary way of thinking, right?" So he had built up that excitement to pursue
Hmm.
that, and engage, and to me also just back then the JEE exams. They were like Olympiad level questions, and
There
there
were,
wasn't
yeah.
multiple choice. You had to really go in
Yeah.
detail, right? Tackle these very hard problems. And so in high school and in pre-university, I really loved just delving into it, because coming from Mysore, right, that didn't have any standardized coaching. I had to
Hmm.
learn a lot with the help of some university professors, and with, of course, the support from back then. It wasn't, the internet was too early. It was still like you had to get the
Correct.
books, you had to study your
Yeah.
books. So, but that at the same time, I'm so thankful I had that, because that's how research is done, right? No one gives it to you
Correct.
ready made. You have to
Yeah.
go and explore, and you
Yeah.
have to figure out ways how things work, and question what is the right way to understand and ground the concept. So yeah, so
Correct.
it was stressful, but at the same time I'm glad I went through that kind of learning, because I think a lot of standardized coaching and testing tends to miss that aspect, right? Like, how do you
Correct.
deeply go into a concept so that even if you're
Yeah.
challenged, even if you are not just solving a very standard problem, but one that is difficult, are you able to tackle it or not?
Yeah. And I think, yeah, the other aspect of a very structured approach could be that, loss of creativity, or not encouraging creativity as much versus preparing yourself. At least that's the
Yeah,
thing which I've seen
because it
in
also
everybody.
inspired me to do research, looking at, I was reading Feynman's lectures in physics,
Oh,
and here I'm at Caltech now, right? That's
yeah.
really my dream. And so I would just read about Marie Curie, and so there was this aspect of, okay, how did people with limited resources back then, when the technology wasn't advanced, how did they come up with this new
Yeah.
discoveries and inventions? And
So
yeah,
true.
so to me,
Mhm.
that's the role of education. It's really looking at other people's journeys and how their quest for exploration, how that led them to where we are today.
Right. And then you, chose to do a PhD in network sensors and use of statistics to kind of find efficient ways to transmit data. So how did that happen? And then I think you also did a lot of research with tensors very early on, right? So can you elaborate a bit more on that, and then where did you kind of apply those, and then what was your PhD days
Yeah, yeah. I mean, the field has moved so much, right? Back then,
like? True.
we
Yeah.
yeah, so it's interesting to look back. And for me, what I again, I love to go from building the foundations and understanding all the concepts, right? And but also not limiting myself to one domain or field. I started with
Hmm.
signal processing, which really is again the foundation of representation learning, neural networks.
Yeah.
Even though many
True.
people cannot think of those connections, and they're also the foundation of the Fourier neural operators we're doing now. So I'm glad I
Yeah.
had the foundation back then. And I started working on wireless sensor networks, which is now Edge AI or Internet of Things. It's gone
Correct.
through different
Yeah.
terminologies. But again, the core concept is right, these devices have limited battery, limited bandwidth. They're continuously monitoring different aspects. How do they make decisions? When to transmit, what to transmit? Do they locally first aggregate amongst different sensors and devices before sending it to, let's say, a cloud or some cluster center, right? Uh, to me, that like kind of framing those different trade-offs of
Hmm.
getting the right information and detecting if there is certain failures, let's say, in the plant that is being monitored, but at the same time looking into energy constraints. I think that helped me think about different trade-offs. And as I was doing that, I realized the importance of modeling that underlying phenomenon,
Yeah.
right? So
Hmm.
because if you can, you know, f- one is to make assumptions of what that would look like, but the other is to learn from data itself. And that's how I
Correct.
got into these probabilistic graphical models, which look at how to model correlations among high
Hmm.
dimensional variables. And, that led me down the path to tensor methods, because the question of how do you model high dimensional probability distributions, you almost always have latent variables or hidden variables, right? You do not
Yeah.
directly observe everything that is affecting that distribution. For instance, I worked a lot on topic models where
Hmm.
if you just have all the uh, text or which now the language models right are able to incorporate, but if you
Hmm.
only wanted some high level topics from them, you don't necessarily want to generate with all the right grammar and everything, but no one has
Hmm.
told you what these topics are, because you may try to label a few of them, but especially if it's also evolving, like in social media, new
Yeah.
topics get brought up all the time, new acronyms, right? So
Hmm.
is there an unsupervised learning method? And that's where we develop tensor methods as theoretically guaranteed and yet computationally efficient methods to automatically discover these topics. And this is also relevant in genetic admixtures, finding communities in social networks, right? Like just a wide
Yeah.
range of applications. And they're still being used today when your goal is not text generation, but just a very quick and cheap aggregation into topics and
Yeah.
that are human interpretable.
And at that time, using GPUs for matrix multiplication, was that being done at that time, or you were actually coding in some other language and building these matrix multiplications in those languages? So what
Yeah,
tools did you use at that time?
yeah, that's a great question. And we made that connection early on, right? Like we said, oh, the reason we went to tensors was first we started with
Hmm.
matrices and we tried our best to make it work with matrices, and there have been
Hmm.
many linear methods like that. And that's not enough, because if you
Yeah.
think about a linear model that implicitly makes a Gaussian assumption. And real world data
Correct.
is very non-Gaussian. And that's when we
Non-Gaussian.
realized, we do need to make these methods stronger, but at the same time, we have to make it computationally efficient. And the
Correct.
classical methods that are likelihood based are not efficient, right? And that was our motivation with going with tensors, that they are parallelizable, they can be run on GPUs. In fact, I have some early work looking into how to do in place tensor contractions on GPUs, right? Like, really, if you think about the general matrix operations, right, there is different
Yeah.
levels of blast. uh, like level one is vector vector operation,
Hmm.
level two is matrix vector, level three is matrix matrix.
Networks
But the higher
matrix. Yeah.
levels you go, right, with tensors, you can get even better efficiency because you can do more blocks and more parallelization. And so to me,
Hmm.
right, that hit me like the tensors are the correct way to go to higher dimensions, keep the computational complexity. And even now, we continue work on that. We've been using tensors to compress layers in deep learning, in
Yeah.
our, all kinds of different architectures there. And I do think as we run into these bottlenecks of hardware limitations, right, we will develop these further, because just with matrix operations and just with the current setup, there's only that big of a model you can
Yeah.
do. There's only that much, right,
Correct.
compute power you can burn. So I do think they'll become even more relevant in future.
So the other thing which I see when I look at your progression is that you've always been there at the intersection of academia and industry, right? So your work with Amazon and now with NVIDIA and earlier with IBM. So was that a conscious choice, or that happened naturally? Because lately a lot of research has actually been driven by industry. So that's more of a recent trend, but you have been on that intersection much before this actually came out. Uh, so can you tell a bit about that?
Yeah, yeah, absolutely. And to those list of companies, I should also add Microsoft. I spent time there as a visiting researcher and collaborator as well. And
Okay.
to me, it
Mhm.
is opportunistic, right? It's looking at what is the best way to make an impact. And,
Mhm.
was clear that there is a lot of really great knowledge, especially in the industrial labs that I started out with. But at the same time,
Mhm.
back then when I was going on the job market first in 2008, it seems ages ago,
Mhm.
uh, you know, learning wasn't done in industry, right? There wasn't a role of like an AI researcher or AI engineer. That those roles didn't
Correct.
exist, and to me, that's what I wanted to work on. I didn't, I want to give that up. And also, when I went on the job market in 2008, it was at the height of the recession. It was,
Right.
like so many job offers were withdrawn, right? Hiring
Yeah.
frozen, and so I was lucky I landed a faculty position, and I was able to see through that. But yeah, but to me, it was clear back then that academia would be the way forward for me to continue to do machine learning. And as more and more opened up in industry and finding those connections, for instance, with tensors, we were working with GPU researchers at NVIDIA and elsewhere even before I joined NVIDIA. And
Mhm.
so, finding those connections is really important, because academia cannot work in the vacuum. And especially now, right? There is
Yeah.
a lot of deep engineering expertise and resources in industry. But at the same time, I do think academia has a very important role to play, especially in thinking about the broader impact of these methods, looking at interdisciplinary
Correct.
connections. We've been honing in on AI for science deeply at Caltech, but also on the
Mhm.
ethical side of it, right? But giving
Yeah.
an unbiased view of where these models are and carefully testing them, right? Looking at their impact, working with uh, right domain experts, whether it's in the sciences or social sciences. I do think
mhm.
academia has a very important role to play.
Right, right. And yeah, completely agree that, the that creative freedom again, industry might kind of narrow it down. So making sure that the work is broad enough, and at the same time, you briefly referred, the ethical side of it is extremely uh,
And,
important.
and I
So,
should say, in my personal experience, NVIDIA has given me the full freedom to work on AI methods that are impactful, look into, right, the scientific domains, especially Earth 2, building the digital twin of our planet for weather and climate models, which is very beneficial to the community. We've open sourced and worked closely with the weather agencies, and so that's a great thing to have. But at the same time, what I'm getting at Caltech is more opportunities to work with many different domain scientists, and most
mhm.
importantly for me, advising students and looking towards the all the next generations, right, and ensuring their success. To me, that's very fulfilling.
Yeah, and maybe actually we'll let's go deeper in what you referred. So, your current work on uh, weather forecasting and use of essentially numerical methods as well as, the AI methods, and then creating harmony of sorts between the two. So, can you share, first of all, the complexity involved in weather forecasting, and I saw through your talk that the acceleration you've got is 45,000 times compared to the models being used. So if you can, elaborate a bit on that, and then how do you see that evolving in terms of, these class of algorithms which are sitting at the intersection of these two different streams, at least at the surface.
Yeah, absolutely. If you look at weather forecasting as an example of traditional solvers, right? How it's done today by the weather agencies is to, from the bottom up, try to model how the atmosphere, right, should behave for what we call medium range forecast for the next 2 weeks, for instance.
Mhm.
And so that involves fluid dynamics, these Navier-Stokes equations, which are partial differential equations, and you're using
Yeah.
all such coupled equations, trying to simulate what it would look like, right, and then combine that with the observations that are present and come up with a prediction. But
Mhm.
the downside of it is each time you're redoing all these computations, and they're expensive, they require big CPU clusters, and it's not just a matter of cost. It's actually potentially hurting our ability to correctly forecast extreme weather events. Because if you think
Yeah.
about hurricanes, wildfires, all these events that are hard to predict, right? What you do is not just take one deterministic forecast. Most likely you will get it wrong. If you say, where will the hurricane trajectory go, right? It
Yeah.
can't be just one single deterministic forecast. What you want are probabilistic forecasts. If you slightly perturb
Right.
the current conditions, how will it change? So you look at all those trajectories, what we call ensembles, and try to come up with a
Mhm.
risk assessment. How likely is it to hit, let's say, Florida? And
Yeah.
so, but right now, with the cost of the current weather forecasts, you barely use about 50 ensemble members in the current systems, the systems that are running today, that do the weather forecasts. And so that limits us. That limits us from capturing those tail risk events, extreme events. Whereas with our weather models using deep learning based methods, because they're extremely fast, you don't need a big CPU cluster. You can just run them on your desktop GPU, and our models are
Mhm.
open source. So you can download them and run them yourself, right? It's democratized. And because it's so cheap, we can now afford our ensemble members to be any number you want, so we can get better
Okay.
statistics. If you
Mhm.
have asked for statistics with just 50 samples, we know that is poor, right? You
Yeah.
need to generate more ensembles. And that's what we are exploring now, how to do that in a meaningful way, how to scientifically show that these methods are also helpful in better ensemble methods because of the how cheap these methods are. So now to delve
Very
a little
interesting.
bit into the deep learning methods itself, the idea is we I know we can use different kind of neural architectures. So instead of trying to from bottom up simulate all the differential equations, we're learning from
Hmm.
historical data, right? And we have a wealth of historical data available, and we can learn to
Interesting.
predict based on that. But our specific architecture also incorporates some of the domain knowledge and constraints. For instance, the fact that the Earth is a sphere. So, can we
Yeah.
incorporate that spherical geometry? And that way, even if we do long rollouts, it captures the fact it's a sphere. And so, as the phenomena
Hmm.
are moving, it kind of, right, it wraps around.
Interesting.
We're also developing methods that can work at different resolutions and take in data at different resolutions, what we call neural operators. And
Hmm.
so those are a principled way to do weather forecasting, solve partial differential equations in different domains. And yeah, so it's great to kind of, come up with first principles AI methods, but also see them have a great impact in practice.
Very interesting. So I, studied computational fluid dynamics as part of my master's, and
Yeah.
I remember, yeah, doing those, calculations on the grid in terms of,
Yes.
solving, let's say, some of the algorithms you mentioned, and every time you had to either make the grid finer or run it at a higher resolution, it used to be so computationally expensive, and making sure that the grid overlay is right, because later on it can create a lot of challenges. So this looks like, this could be a way to kind of reduce those computations significantly, and then still achieve very finer level accuracies in that sense.
Yeah, yeah, absolutely. You're spot on there, and indeed, right. What numerical solvers try to do is get to a really fine grid, iterate over space and time, depending on, let's
Exactly.
say, for fluid dynamics, and they need to do this lots of iterations to converge to the solution. But the way
Right.
we do with machine learning based methods, neural operators, is instead to learn new basis functions. So you don't need a fine grid, right? You can get away
Hmm.
with a much lower amount of computation. And to me, right, ultimately, this is the only way to solve some of the hardest challenges we are facing today. For instance, with the climate modeling, in the climate models, what you need to capture are these what we call cloud turbulence. So they need a very fine grid. In fact, the computational expense is so great that they can't fit on any of our biggest supercomputers. It's about
Hmm.
100 billion times more computing than
Wow.
what we have on the planet today, right? If we really
Wow.
want to resolve all of those cloud dynamics. And indeed, machine learning is not there yet to do that. But to me, we have to harness machine learning to explore how to solve those kind of hard challenges. And these are great stepping stones for that.
Wow, great. And any other areas or applications where again you see this intersection and these kind of algorithms accelerating the work? So weather is definitely one. Any other area which you've come across
Yeah.
where you're using the same techniques?
There's so many areas, right? So if you look at partial differential equations, I think Steven Strogatz calls it the workhorse of
Hmm.
of everything of science and engineering.
Yeah.
And first of all, with the weather forecasting itself, I do want to also mention to the listeners here that we have the model working uh, at the ECMWF website. So that is the website that has premier weather forecasting systems. And so you can side by side look at the charts and look at, oh, how is our model doing, the machine learning based model, and how is the current forecasting system doing. And so
Oh, very
meteorologists are
interesting.
already studying those. There was a Washington Post article last week about how these machine learning models are able to accurately predict hurricanes well in
Hmm.
advance, and uh,
Oh, wow.
able to do well. And so I do think it's going to be a very already I'm very surprised to see how quickly these models went into the
Hmm.
actual system. So this is not just
Systems.
right a paper or just a concept. This is working on the current weather data, right, in real time, providing forecasts. And so I know I'm very excited to see that. But in addition, these partial differential equations are everywhere. Another application we're very excited about is carbon capture and storage. And indeed, these technologies are still nascent and there's a lot of challenges, right? But one important challenge is, where would you store the carbon dioxide, and how easy is it to capture it in underground reservoirs? Which reservoirs are the best place to do that? And over time, especially several decades, how will that gas plume, if you pump carbon dioxide into water, over time, how will
Hmm.
it change and what will happen, right? Ultimately, how much carbon do you capture through these
Hmm.
whole system? So we are helping that evaluate in very high resolution. So this would have taken more than 2 years with the current numerical simulators if we try to do a full probabilistic assessment. But instead,
Hmm.
on our neural operator based machine learning system, it took about 2 seconds. So
Oh,
that is,
wow.
to me, such a big speed up, right?
Right.
About little less than a million times speed up. So
Wow.
that is just exciting, and I think that's where we'll see all the bigger advantages as we keep going to higher and higher resolution problems, right? Higher fidelity, or require these probabilistic assessments that would require a lot of iterations, or a lot of ensembles with the traditional solvers that would be too expensive. And so, yeah, so to me, I see so many such possibilities. We've been working for predicting disruption in nuclear fusion. We've been looking at ultrasound beam forming, material deformation, seismology, so all kinds of problems, and as
Oh,
well as
wow.
inverse, yeah, and as well as, so it's not just simulation, but as well as we're
Hmm.
doing design. So, for instance, we recently invented a new design for a medical catheter, which is a pipe. What you do is you draw fluids out of the human body, right? If somebody is a patient in a hospital or
Hmm.
so, you use this, and but there is this risk of bacterial contamination because bacteria tend to swim upstream to the fluid flow. And what we came up with is a simple way to try to prevent that bacteria from swimming upstream, which is to add like triangular shapes inside the pipe. So, and that
Hmm.
creates interesting vortex phenomena that doesn't let the bacteria swim upstream. So it is complex fluid dynamics, which you would appreciate given your
Yeah.
background there, right? And if you try to do this trial and error in terms of, oh, what is the optimal triangular shape, this would require a lot of physical experimentation and back and forth. But instead, what we
Correct.
did was to simulate it with neural operators and let machine learning through gradient descent come up with the best design, right? What is the best shape of
Wow.
triangles? And so
Hmm.
then it was just only one step. We went ahead, 3D printed, and did other
Wow.
microfluidic experiments. We validated it. So I think that's, to me, the aspect where this has such a large potential, because if you can reduce the physical experimentation and do as much as possible with
Yeah.
within the virtual realm, and with accurate simulations, if you can invert the process because these machine learning methods are differentiable, you can come
Wow.
up with great design candidates, and even those that maybe humans find it hard to imagine, or maybe they haven't explored because it's too risky, right? So that
Yeah.
really opens up a lot of possibilities for us.
Yeah, I think those possibilities are countless in the sense, we are, for example, and I'm just making it up probably that we're assuming it to be a triangle to be the best shape, and then machine learning could actually show that it's a different shape. So,
Yeah, and in
uh,
fact, machine learning also proposed polygons and all kinds of more complex shapes, but we asked
mhm,
it to limit to triangles because of the ease of 3D printing, and we wanted to just kind of keep it simple in the beginning. And yeah,
mhm.
so there's certainly lots of possibilities, right? And much more other kind of three-dimensional shapes and other applications. So to me, this is just the beginning.
Great. And how do you see this evolving, let's say, over the next few years, this intersection? Do you see this becoming more and more popular in the research streams, or any specific kind of areas which you kind of feel would make a huge impact in, let's say, next few years?
Yeah, absolutely. When we started AI for Science at Caltech, I think in 2018, it was still the early
Hmm.
days, right? And everybody wanted to do AI on mostly vision, computer vision.
Yeah.
Some text was starting up. But now, there is so much development in the scientific domains. Of course, there is the protein folding models of the world. There is all kinds of new drugs being designed. So there is now a lot more awareness that this is, right, a very fruitful research path, and one that has a lot of opportunity if you're a domain expert to use that, right, in to with machine learning to make a big leap from where how things are done currently. And so I see a lot of openness and excitement. So I would say that AI for science is something that, if you're now thinking about starting on a new research topic, it's a great one. But also for industry, there's so many areas, but especially I think it's starting in the life sciences, but it will propagate to many other domains of engineering and sciences.
Very true. And just the diversity of projects you're working on, and for each of these, you would be coordinating with the subject matter experts. For example, you mentioned the weather expert. So, uh, I mean, how does that a typical project go? So, do you spend a lot of time upfront learning about the domain, or how does that whole equation work in terms of picking up a new domain and then going deep in it?
Right. Right, absolutely. There is a lot of close interactions with the domain experts, but especially after, right, us coming up with neural operators as a way to solve partial differential equations, the bar is much lower, right? Because so many of these are already expressed in that form. And so, in that sense, they're low hanging fruits. But in many other domains, you may not have those full specifications, and there's a lot of other knowledge that's not captured in the equations. And so those are the next realm of things we are getting to now. So it's, to me, like, coming up with a method like neural operator, the benefit is you're solving this grand challenge of different partial differential equation systems, and then using these applications as a way to test how well these methods are doing, take feedback, right? Coming up with better neural architectures or optimization and training schemes, all kinds of ways that we can improve because we are challenging them on much larger scale, real world, industrial scale problems. So that's how I see it.
Great, great. And just touching about something which is slightly more recent and largely due to interest of time, but we can kind of spend a lot of time on this. But I just want to move to the the paper you presented in NeurIPS last year, which was also awarded the best paper about mind dojo. So can you I can describe it, but I think it's best if you can share what that paper was about, and because I think it is truly groundbreaking in terms of the work which has happened there.
Yeah, yeah. Thank you for bringing it up. And I want to frame MineDojo and few other works like that. We have Voyager. We have what is known as Weimar. So all of those, right? think of using foundation models, whether it's text or image or videos. So models that have learned on large scale data sets and generally understand text and other modalities. So how do we use that to solve problems with decision making, where you need to interact in an environment, explore, solve many different tasks? So what we call open-ended learning, where the goal is not just to solve one task and be done, right? There's continuously new skills to be learned, new tasks to be performed. And that's where when framed MineDojo as a benchmark and a suite of essentially different tasks that is in Minecraft environment. Minecraft
Yeah.
is a game, so why pursue Minecraft, right? There have been so many other AI on different games, but the reason
Yeah.
is precisely what I mentioned. It's for open-ended learning. So you're
Open.
not just finishing one task and declaring success. You continue
Yeah.
to, build, solve all kinds of new ones. There's a lot of creativity in that game. People have
Yeah.
built CPUs and GPUs and castles and all kinds of
Correct.
impressive structure. And so to me, right, it's infinite possibilities. And so there's always more and more aspects for any deep learning method or AI method to be challenged against. And that was our motivation to create that benchmark.
So basically, MineDojo is if you have to describe it, West, it's a library of these benchmarks. Is that the right way to kind of put that?
So I would say MineDojo is having Minecraft as the environment in which you test your algorithms, right? And we already
Right.
have some algorithms in the repository that look at joint image and text models, for instance. And in
Yeah.
our latest work with Voyager, what we did was through it's known as the MindFlayer API for Minecraft, we
Mhm.
hooked it up to GPT-4 and asked GPT-4 to come up with instructions on where do you think the agent should go next, right? And the agent goes and tries different actions, comes up with feedback, and then again, right, tells GPT-4. And so you kind of like do this interactive in context learning uh, with the use of the large language model. And in addition, you're also using these language models to suggest what to do next. What is that
Mhm.
automatic curriculum here? What do you think is an easier task, and what should I do next? What should I solve next? And as you're doing that, you build up a skill library, and when there are new tasks, you again go and look up your skill library and say, oh, maybe this is relevant here, this is relevant, I should combine these together. This is how education works, right? There is a
Right.
curriculum. You go explore, you try to solve problems, you look up the skills you've developed. So it very much has the philosophy of lifelong learning that we have built into Voyager, and use Minecraft as a testing ground to showcase these capabilities.
And it also feels like, if I look back at maybe how computer vision has evolved, right? Almost creation of ImageNet was probably equivalent in terms of what this is, right? So in a few years, in all likelihood, this work which has happened would fuel in a lot more, this algorithms on decision making and in benchmarks. Is that
Yeah, that's our hope.
the
And, we are seeing a lot of great adoption there. And, right. And not just one class of techniques. There's reinforcement learning people are trying to do on the benchmark. But as I said, you can just use pre trained language models without any fine tuning, interact with it, and see how well you can solve the task. Right. Or now there are efforts to combine both of them. And to me, I think it's important to look at, for the future of these interactive learning, all of these algorithms together. And that's what this offers. Because for the longest time, reinforcement learning was successful in some limited single task domains, but also it required
Yeah.
enormous computing. AlphaGo, right? I mean, still used human information, and if it's AlphaGo zero, it's right much more expensive. And so reinforcement learning by itself gets stuck in all kinds of problem solving. Whereas
Yeah.
language models or now multimodal models could really give you suggestions, but maybe they're wrong, right? They're not always correct.
Hmm.
And
Yeah.
this is still, if it's a new task, it's not going to completely solve it by itself. So you do
Yeah.
need some combination of all of this. And that's the work we are doing, in this thread. And that's very exciting.
And right now, it essentially works on these text instructions and carries that out in the game environment. Is that
Mhm. Mhm.
interesting? And
That's how
uh,
Voyager framework is working. Yeah.
great, great, great. Uh, uh, thanks a lot, Anima, for sharing those insights. We are running out of time, but it feels like I could have probably a few more episodes discussing each of these streams with you. But just a couple of last few questions, and these were some questions which community members shared. So we mentioned it to the community that we'll be doing this podcast. So the first question was for aspiring AI researchers or students who are just looking to build their careers in this domain. What are some of the areas you would suggest them to focus on to essentially make significant contributions to the field in future?
Yeah, I would still always emphasize on fundamentals, right? Because there may be the
Yeah.
notion, oh, these language models already know everything. Why should I learn this? Or why should I learn to program? Or why should I
Mhm.
learn to, go through all the concepts in machine learning and AI? And to me, the answer is yes. I mean, maybe write all of the syntax in every programming language you probably don't need, but it's all
Mhm.
about the concept, right? What is the
Yeah.
algorithmic thinking? How do you frame the steps in a procedure, and which one is more efficient compared to others? And I
Mhm.
think that's still relevant because even though these language models are getting better at coding, they're still going to be guided by us, right? And
Yeah.
so I think of this as now a higher level abstraction. Just as now we are
Mhm.
not coding in assembly anymore, right? We were in the
Yeah.
very early days of computing. We've
Correct.
been building higher level abstractions, and the latest one could be also adding language models. But the problem is with language models, they're also error prone, whereas the earlier abstractions,
Yeah.
at least you knew, right? They would function as expected.
Correct.
So that
Mhm.
brings up new challenges, and there's going to be a lot of the human in the loop. Oh, when should you use these AI tools? When should you not? And so, in order
Mhm.
to build them to be more robust or design how all of these human interactions work, there's a lot of new research to be done, a lot of new development products to be built. And so I would still emphasize the fundamentals, because if you don't understand how these models work, you wouldn't be able to do research on it, right? Maybe you can still use them, but to do research, you still need those fundamentals.
Interesting. And then, among the problems you've seen, and specifically, the scientific problems, which one do you think is the hardest one to solve with the current resources and technologies? What would it take to kind of crack it, if that is clear?
Oh, there are so many, right? I mean, there are some problems that are purely computationally bound. So, meaning if you
Hmm.
had enormous computing, we know the equations, you would be solving them.
It
Those
will
are
be
climate
solved.
models that I mentioned before, assuming
Yeah.
you accept that, right? It's driven by
Hmm.
these equations. And quantum chemistry, where it's again the Schrodinger's equation, but it's exponentially growing. You just cannot afford to do it with the current computing on any reasonably big system, in an exact way. But if we were to able to do it, we could solve instantly all the aspects of material properties, drug properties, right? Come up with
Yeah.
optimal material or drug for
Mixture
any
of
use.
materials. Yeah.
So that would solve all the problems, but that's difficult. So that's one bucket of problems that's purely about compute. And then there are
Mhm.
others where we don't know the full model. I mean, any kind of
Correct.
higher organism, we're barely trying to understand, okay, how do molecules and proteins bind? Even there, it's not perfect. But the minute you keep going above, how do cells, processes in a cell, can you describe every one of them, right? How do cells
Yeah.
kind of organize
Correct.
themselves? I mean, there's so limited understanding of those mechanisms, right? And we are very much relying on physical experimentation because so many models are wrong. And so that's the question. We do need more data, but if we try to improve our modeling capabilities through limited data, what else can we do? And yeah, and then there are others that are a mix of physical experimentation and simulation. Nuclear fusion comes to mind, where
Mhm.
predicting disruptions is extremely hard. But at the same time, if you try to do it with physical experimentation and try to push it too close to it, that's not good,
Yeah.
right? You have to,
Not good.
you can do more explorations in virtual world. And in
Virtual
fact,
world.
one of proposals we're collaborating is to try to explore like a stellarator design, a completely different way of designing, like more almost like a donut compared to how current fusion reactors are built. But again, there is so much more we can explore in simulation before we bring it to the real world. The cost will be lower. And yeah, so these examples come to mind, but there are just so many more like this.
Wow, great, great. And thanks for sharing that. Is almost so energizing to see the impact which can be created in the next few years, and then really, hopefully in a few years in future, we would probably discuss the impact created by some of the work you're doing. So thanks a lot, Anima, for taking time out and then for doing this discussion.
Yeah, thank you. Thank you for having me. And, we do need everyone, right, who's interested to work in these interdisciplinary areas. That's how we maximize the beneficial impacts of AI. And thank you for all the good work you're doing at Analytics Vidhya.
Thank you. Thanks, Anima. Thanks a lot.